Now let us go to Electromagnetic Induction lesson 4. It is a theory and very important. Now, now look, we know flux symbol was phi was defined as B dot A, magnetic field area vector, magnitude of B, magnitude of A, theta, angle between the magnetic field and area vector. Now from this, if you bring A cos theta to this side, your B becomes phi over A cos theta. This is the component of the area vector through which the magnetic field lines are normal to it. Now this phi is in the numerator and this is a fraction. So if phi increases, B also phi increases, B also increases. If phi decreases, B also decreases. Now, now from this equation 1, we conclude phi depends on B, A and cos theta. From 1 it is clear phi, the magnetic flux phi, depends on the magnetic field, magnitude of the magnetic field, area vector, theta or cos theta. And we also know from Faraday's law that EMF produced is E is equal to, due to change of flux, minus n d phi by dt, where phi was the flux changing with respect to time, n was the number of turns in the coil, minus sign was indicating the direction of the current. So if you look at, since phi depends on these three things, so phi can be changed in three different ways by changing B, A or theta in three different ways, as it depends on three different parameters B, A and cos theta. And EMF depends on phi. Phi can be changed in three different ways. So EMF E can be produced in three different ways, by changing B, by changing area or by changing the theta, that is the orientation. Therefore EMF can be produced or induced in a coil or conductor in three different ways. Number 1, by changing B, by changing the magnitude of B. Number 2, by changing the area vector. Or number 3, by changing the theta between the magnetic field vector and the area vector. Now look at this diagram. Y flux was defined as B dot A, that is BA cos theta. Flux by definition is number of lines of force, magnetic lines of force in this case, passing through the area vector normally. Now if it is not normal, if the lines of force are not passing normally, then what we have to do, we have to take the dot product. By taking dot product, the lines of force automatically becomes normal. This BA cos theta can be written like this or can be written like this. This is same thing as equal to this. The meaning here is the component of the area vector A cos theta is taken. Here the component of the magnetic field B vector is taken. So now this component A cos theta becomes now the magnetic field lines B will pass through A cos theta normally. Here the component of B cos theta, that is, this becomes normal to A. That is clear from the figure. Let me explain you. Here this shaded area, the yellow area, is an area pointing to this side because this is the outward normal to the area that gives the direction of this yellow area. Now suppose the magnetic field is to this side, magnetic field line shown in red is to this side, and this area vector is to this side, A. Theta is the angle between them. So these magnetic field lines B, these lines, they are here also, 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 they are here also. They are not passing through this area vector normally. So what you have to do, so if this is the area vector A, then this is your A cos theta. So A cos theta means the component of this area vector A cos theta like this to this side. A cos theta is to this side. Now these magnetic field lines B are passing through this area vector. This area is same thing as this area, but this area is the component, A cos theta component of this area. And what will be A sin theta component? A sin theta component will be pointing this way. So here through A cos theta, all these magnetic lines of force B are passing normally. Similarly, the area vector is here, A. This is the magnetic field lines B. This angle is theta. So I have taken B cos theta. Now B cos theta. Now B cos theta. If B is to this side, B cos theta is to this side. So from the area vector, this area, if I draw it here, from this area, this B cos theta is passing normally. So that is how flux is defined as B dot A. Means if the lines of force are not passing normally, then you take the dot product. Now then first, how to produce EMF by changing the magnitude of B. From here, phi was depending on these three things, EMF was depending on phi, therefore EMF depends on these three things. Means EMF can be produced by changing B or A or theta. So let us go to the first one by changing B. Now, by changing the magnitude of B, how EMF can be produced. Now look at these magnets, north pole, south pole. These red lines are the magnetic field lines. Here is a coil. Now, I just explained B is equal to phi over A cos theta. Now this is your area vector. When the magnet is here, the number of lines of force passing through this is less, means phi is less. So B, due to this magnet, the magnetic field here is less in this position. If this magnet moves to this side, then through this area, more number of lines of force will pass. That is, flux increases, therefore B increases. So by moving this magnet towards the coil, the magnetic field here increases. If you move this magnet towards this side, the magnetic field here decreases. Similarly, you can do it the other way. If the south pole comes to this side, magnetic field B here increases. If you bring the south pole to this side, magnetic field here decreases due to the increase or decrease of flux. So, and that is what I had explained. When this north pole is coming towards, flux is increasing. So EMF has a value, d phi by dt has a value, so EMF is produced. And the current is anti-clockwise according to Lenz's law, because if the current becomes anti-clockwise from this side of the coil, this will behave as a north pole. So it will push this north pole to this side, means it will try to decrease the flux. As the north or south pole moves towards the coil, phi increases, that is B increases. So by changing the magnitude of B, EMF is induced, and that therefore there is a current. Now the second part is very important, by changing the area. Now look at these two red lines. This red line and this red line is a rail on which the conductor PQ, this conductor PQ can slide like this or like this. It can slide like this towards the left or towards the right. And these black crosses indicate the magnetic field lines are into the plane of the paper. This indicates in this region there is a magnetic field which is into the plane of the paper. Means the field lines are passing through the piece of paper, but normally into it. PQ, a conductor that can slide on the rail. This PQ is a conductor that can slide on this rail. This, and these are two parallel rails on which PQ can slide like this. Now look, when PQ is at PQ, when PQ is here, PQ is a conductor, when PQ is here, don't look at P dash Q dash now. When PQ is here, no lines of force are passing through this because it is not creating any area. When PQ is at PQ, it is not creating any area. So the flux, let it be phi 1, be a cos theta, since A is equal to 0, and theta is 0 because magnetic field lines are into it. So this becomes, whole things becomes 0. There is no flux when PQ is at PQ. Now PQ is at P dash Q dash. When it is moving with a velocity v, after some time it arrives at P dash Q dash. When PQ is at P dash Q dash after time delta t, when PQ moves from PQ to P dash Q dash in time delta t, It is creating this area, look, P, Q, Q dash, P. This area it is creating, and through this area, some lines of force are passing through this normally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is what I have explained. When PQ is at P dash Q dash after time delta t, it is creating an area PQ, Q dash, P, and some, in this case 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 magnetic lines of force are passing through this area normally. This I just told you to explain. Now, so there is some flux. So implies final flux. Phi 2 is equal to final flux, which had some value, right? So there is a change of flux because when PQ was at PQ, no lines of force passing through this because it is not creating area. When PQ is at P dash Q dash, by moving with a velocity v after time delta t, it is creating an area PQ, Q dash, P, and through this area, some lines of force are passing through normally, so there is a flux. So initially there was no flux, now there is some flux, so there is a change of flux. So there is a change of flux. So there is a change of flux and EMF is induced. Hence, EMF E is induced because there is a change of flux. Now, let us calculate it mathematically. Let L is equal to length of PQ. Let L is equal to, from here to here, the length of this conductor is equal to L. At t is equal to 0, it is at position PQ. At t is equal to delta t, it is at position P dash Q dash. And v is equal to its velocity. V is equal to velocity of PQ. So this distance, P dash, Q dash, will be velocity into time. So let P dash, Q dash, P dash, Q dash is equal to delta x, a small distance. Therefore, this area Q dash, P dash will be this length into this breadth. From here to here I have taken it as delta x. From here to here I have taken it as L. So it will be L into delta x will be this area. So L into delta x will be the area. So the area Q dash, P is equal to L delta x. L remains as L, delta x is the distance, that will be equal to speed into time. All the lines of force passing through this area normally because theta is 0. Now this area is, now all the lines of force are passing through this area normally. So the flux is equal to, so now the flux phi 2 is equal to BA cos 0, that is BA. For A I write LV dt. So this is your second flux. So the change of flux, let it be d phi, will be final flux minus initial flux, that is this minus 0, that is equal to BLV delta t. Now EMF is defined as d phi by dt. The negative sign I have not taken, I am finding out the magnitude part of it. The negative sign only indicates the direction of current, that I will discuss in the next phase. For d phi I put this BLV delta t. For dt I write delta t because it traveled from this position to this position in delta t time. So change of flux divided by time, delta t cancels, so BLV. So EMF produced is equal to BLV. So when the conductor moves, cutting the magnetic lines of force are into the plane of the paper. If the conductor moves like this, cutting the lines of force perpendicularly, moving with a velocity v, the EMF developed is BLV. B is the magnetic field, L is the length of the conductor, V is its velocity. Now the question is, now what will be the direction of the current? Now is important. When PQ moves from PQ to P dash Q dash, flux increases. Now let me show the picture again. When PQ moves from PQ to P dash Q dash, Initially the flux is 0. Now when it is moving from here to this position, the flux is increasing. So when PQ moves from PQ to P dash Q dash, flux phi increases. According to Lenz's law, the direction of current should be such that the flux should decrease. Now, when PQ is moving from PQ to P dash Q dash like this, the flux is increasing. Here it is 0. When PQ is here, the number of lines of force passing through this area is 1, 2, 3, 3. When PQ is here, this is the area created. Then the number of lines of force passing through is 1, 2, 3, 4, 5, 6. So as it is moving to this side, the number of lines of force passing through the area it is creating is increasing. So according to Lenz's law, if this conductor experiences a force to this side, then the flux will decrease. Then how this conductor PQ will experience a force to this side? That is the question. So according to Lenz's law, the direction of current should be such the flux should decrease. That is the conductor PQ should experience a force to this side. And a force will be possible to this side only if PQ carries current in this direction, by using the expression F is equal to IL cross B, which we studied in magnetic effects of current. If you take the current from P to Q in this direction, current P to Q, magnetic field is into, so IL is to this side, magnetic field is to this side into, so IL cross B will be towards the right. So if the current is from P to Q, this conductor PQ will experience a force to this side, therefore the flux will decrease. That is, PQ should experience a force towards right using F is equal to IL cross B. That is, the current is from P to Q. Now what will be the current? So that is how the direction of current. And current is voltage by resistance. And the voltage is the same thing as EMF that we derived as BLV divided by resistance of the conductor. Now this PQ, I have shown it here. When this PQ was moving in the magnetic field like this, the EMF developed was BLV and the current is from P to Q. So what is the conclusion? The moving conductor PQ in B is behaving as a voltage source of EMF BLV. Means you can replace PQ by a battery like this having EMF BLV, and the direction of current is like this. Now, so that is all about